Hello everyone, welcome to this lecture. The plan for this lecture is as follows. In this lecture we will continue our discussion on finite fields and we will discuss what we call as order of a finite field and what are the properties of an order of a finite field. So, basically order of a finite field is the number of elements in your set F, if F is the field, and we can prove a very strong property, a very strong statement regarding the order of a finite field. So, the statement here is the following: imagine your field F is a finite field and suppose its characteristic is P. Now, as per the discussion that we had in the last lecture, we know already that this number P is a prime number. What we can prove actually is that the number of elements in this field is of the form P to the power r, where r is greater than equal to 1. Okay. That means you take any prime field, its order you take any field, any finite field, sorry, not prime field, you take any finite field, the number of elements in the field will be of the form P to the power r, where P is a prime number and the characteristic of your field. Before going into the proof of this theorem, you can recall easily that the fields that we had discussed in the last lecture, we saw there a field consisting of 9 polynomials, its cardinality is 3 square because its characteristic was 3. In the same way, we saw the abstract field consisting of 4 symbols, its cardinality is 2 square because the characteristic of that field was 2. If you take the field ZP, okay, its cardinality is P power 1 because its characteristic is P and so on. So, it is not the case. So, what we are actually going to prove is that it is not the case that it is happening accidentally only for F9, F4, ZP, but you take any prime any finite field with characteristic P, the number of elements in the field will be of the form P to the power r. So, before going into the proof of this theorem, we are going to introduce some notations which we will be using in the proof. So, remember the additive identity of the group is 0 and the multiplicative identity of the group is 1. I will use the notation n with a different font here to denote the element which I will obtain by adding the multiplicative identity n number of times. Okay. So, typically in regular integer arithmetic, where this element 1 is the numeric one, if I add 1 to itself n times we get n, but this element 1 need not be the numeric one, it is the multiplicative identity. If you add itself if you add this element 1 to itself n number of times, then as per the closure property of the field you will obtain an element from the field. That can be any abstract element, but just for the sake of simplicity I will use this notation n with a different font to represent the result of 1 added to itself n number of times. In the same way, 1 added to itself p number of times will be represented by this special font p, and since the characteristic of the field is p itself, this element p with the special font is nothing but the element 0. Okay, that comes from the definition of the characteristic of a field. In the same way, if I take any abstract element, arbitrary element f from the field and add f to itself n number of times, I can obtain the same result by saying that each of these f's can be replaced by the product of 1 and f, because 1 is the multiplicative identity and this I am doing n number of times, and then I can distribute the plus over dot, and 1 added to itself n number of times as per my notation is the special font n, which is a element from the field, and that element multiplied with f will be the overall result, right. So, now let us go into the proof of this theorem. Okay. The proof is very interesting here. So, you consider any element of the field and any multiple n from the set of natural numbers. My claim is that the operation or the result of adding f to itself n number of times, which will give me this element special font n dot f, is also an element of f, and that comes from your closure property, right. So, as per our notation, as per our definition, the element n added to itself f will give me this element, and as per the closure property, this element will be an element of the field itself. Now, what are the relevant values of n? Relevant in the sense which will give me non-zero elements. So, the relevant values are 0 to p minus 1. Okay. By relevant I mean only those multiples which will give me distinct elements. Okay. So, 0 times f will of course give me the element 0 as per the definition. Now, f added to itself, or 1 times f actually to be more precise, is just the element f. Now, f plus f will give me some element from the field. So, I can call it as 2 times f. This is not a numeric 2, but some 1 added to itself 2 number of times, that is a representation here. And like that, if I continue, then I can say that f added to itself p minus 1 number of times will give me p minus 1 in special font dot f, and after that if I add f to itself once more, I will get the element 0, because p is the characteristic of the field. So, in that sense, the only relevant multiples of f are 0 to p minus 1. Okay. Because after that you take the higher order multiples of the element f, you will start getting the same elements which you could have generated by taking the multiples of f in the range 0 to p minus 1. Okay. Next, let me define what I call as the span of the field. So, a collection of k elements, right. So, here is your field f, which is finite and which has some number of elements. So, if I focus on a collection of values which I call as f1, f2, fi, fk, I will call the collection of these elements as the span of the field. If the following hold, you take any element x from the field, that can be expressed as a linear combination of the elements from your collection f1 to fk, where the linear combiners are from the set 0 to p minus 1. Why I am focusing on the linear combiners which are in the range 0 to p minus 1? Because as I said here, the relevant multiples of any element from the field are where when you take the multiples to be in the range 0 to p minus 1. Okay. So, basically span means that it is actually the subset of those elements from the field in terms of which you can express any element of the field, okay, by taking various linear combinations. And when I say linear combination, by that I mean that I am doing the plus operation and the dot operation as per the field. So, it is easy to see that a trivial span of the field is the entire field itself, right. You take any element x from the field, that can be always represented as 1 times x plus all other elements being multiplied, all other elements from the field being multiplied 0 with 0. Okay. So, 0 times the first element and so on. Okay. So, that is why the entire field is of course a span of itself. Now, let me next define what we call as the minimal spanning set of the field. So, the minimal spanning set of the field is the collection of elements from the field which is minimal in the sense that you cannot remove any element from this collection. if you remove any element from this collection, then it is no longer the case that reduced collection still spans the entire field. That means, no proper subset of this collection spans the entire field F. In that sense, it is minimal, it is essential collection. Okay. And there could be multiple minimal set spanning your field. It is not the case that it is always unique. It may be possible that a collection of first 3 elements from the field constitutes a minimal set spanning the field, or say the last 2 elements from the field, they are the essential elements and so on. Okay. Now, why I am focusing on value r here, because remember our goal is to show that the order of the field is of the form p power r, that is why I am taking r here. So, I am basically saying that a collection of r elements from your field F will be considered as a minimal set spanning the field if it is the bare minimal collection of bare minimal collection of elements whose presence is required to express every element from your field as a linear combination. Now, what I am going to define is the following. I am going to now define a mapping G from the set ZPR to the field F. Now, what is the set ZPR? So, as per the definition of Cartesian product, ZPR is nothing but the Cartesian product of ZP with itself R times. That means, if I consider an R tuple present in ZPR, then by that I mean that I am talking about R elements where each of the elements are from the set ZP. Okay. Now, how exactly this mapping G is defined? So, if you want to map an R tuple as per the mapping G, then what basically you have to do is the following. You have to take a linear combination of the elements in your minimal spanning set as per the linear combiners in your R tuple. That is the way I have defined my mapping G here. Okay. So, right now I am not making any claim about this mapping G, whether it is injective, bijective, surjective, it is just a function. Okay. Right now I am just giving you the definition of the function. The definition is, you give me any R tuple, then I will match that R tuple to a finite field where the mapping is obtained, or where the image is obtained by taking a linear combination of the elements in the minimal spanning set as per the linear combiners in my R tuple. Now, I am going to make certain claims about this function G. I am going to prove that this function G is a bijection, and if it is a bijection, then as per the rules of cardinality, it shows that the cardinality of F is same as the cardinality of ZPR. And what is the cardinality of ZPR? The cardinality of ZPR is nothing but p power r, because as I said, the definition of ZPR is you take the Cartesian product of ZP r times. So, there are p power r possible elements, or p to the power r number of R tuples present in the Cartesian product of ZP r times, and assuming that G is a bijection, which I am going to show, assuming that this statement is true, it shows that the cardinality of F is same as the cardinality of ZPR, and hence it shows that the number of elements in my field F is some p power r. Okay. So, that is a proof strategy here. Now, everything boils down to proving that my mapping G is indeed a bijection, and as per the definition of a bijection, I have to prove that the mapping G is a surjection and it is an injection. Well, proving that G is a surjection is trivial, that comes from the definition of your spanning set. Since as per my definition the collection F1 to Fr is a spanning set, that means you give me any element x, it will have a pre-image. Why? Because as per the definition of a spanning set, this element x can be expressed in terms of these R elements as per a linear combination, where the linear combiners will be from ZP, and how many such linear combiners I will need? I will need R such linear combiners, and if each of them is an element of ZP, basically the collection of the corresponding linear combiners is going to be an R tuple from this set ZPR. So, that trivially proves that this function G is a surjective function. Now, I want to prove that this function G is also an injective function, and that I will prove by contradiction. Okay. So, as per the contradiction, assume that the mapping G is not injective. That means, imagine you have two different R tuples. So, you have an R tuple say N1, N2 and R, which is different. Okay, so, let me write down this different R tuple here itself, because I will need this space. So, imagine you have two different R tuples N1 up to NR and another R tuple M1 up to MR, and say both of them gets mapped to the same element X as per the mapping G. What does that mean? It means that you take the linear combination of the elements of your spanning set as per the combiners N1 to NR, and if you take the linear combination of the elements of your spanning set as per the linear combiners M1 to MR, you get the same element, same field element. That is what it means when I say that the mapping G is not injective. Now, if this is the case, I have to arrive at a contradiction. Basically, I will try to arrive at a contradiction that the collection of R elements which you assumed to be the minimal spanning set is actually not a minimal spanning set. That means, there are some unnecessary redundant elements which have been added unnecessarily in this collection, which can be simply removed. I will arrive at that contradiction. How do I arrive at that contradiction? Well, what I know about these R tuples is that they are different. That does not mean that the entire R tuple are that the entire set of the entire R values in the first R tuple and all the R values in the second R tuple, they are different. There might be some of them which are same. So, it might be the case that say the first R elements in both the R tuples are same. So, you have say N1 N1 and N2 N2 occurring. But suppose I is the first index, where in the first R tuple you have the value Ni, and in the second R tuple you have the value Mi, where Ni and Mi are different, but the first I minus 1 components in both the R tuples, suppose they are the same. So, I am focusing on the first index I, where the R tuple n and the R tuple m, they are different. That index I could be any index in the range 1 to R, and there definitely one such index I, because as per my assumption the entire n tuple and the entire m tuple, they are different. So, if they are completely different, definitely there must be some component, some index I, where the component in the n tuple and the component in the m tuple, they are different. I do not know what exactly is that index, but that index I definitely exists. So, I am focusing on that index I, and assuming that the first I minus 1 components, they are same in both the n tuple and the m tuple, then I can cancel them out both from the LHS and the RHS, because if I have N1 times F1 occurring in the LHS and imagine M1 is same as N1, then I can cancel out N1 F1 from both the sides. In the same way, if N2 is same as M2, I can cancel out N2 and F2, N2 times F2 and N2 times F2 both from LHS and RHS and so on. But then when I come to the ith term, what I have done here is I take the term Mi times Fi here to the LHS here, and whatever is the remaining part of the expression in the LHS part, I took it and bring it in the RHS. I have simply arranged the terms here, right. Now, if this is the case, if I get this equation, what I can say is the following. If I multiply both the sides of the equation by the multiplicative inverse of this element, okay, and the multiplicative inverse of the element Ni minus Fi exists, because as per the definition Ni is not equal to Mi, that means Ni minus Mi is not 0, and if it is not 0, then as per the definition of a field, I do have an multiplicative inverse of this element. That means, I do have an element which I can denote by this notation, which when multiplied with the difference of Ni and Mi will give me the multiplicative identity, namely 1. So, if I multiply with the multiplicative inverse on both the sides, I basically get the fact that Fi can be expressed in terms of Fi plus 1, Fi plus 2 and Fir. That means, it shows that I can remove Fi safely from my supposedly minimal spanning set of F. It is not necessary to keep Fi in this collection, because I can express Fi in terms of the remaining elements in this spanning set, which spans the finite field F. And that goes against my assumption that this collection of R elements F1 to Fr was the minimal spanning set of the finite field. Okay. And why I came to this contradiction? Because I assumed that my function g is an injective mapping. So, that shows because I assumed that the function g is not an injective mapping. So, that means whatever I assumed about g is incorrect, and that shows that indeed my mapping g is an injective mapping, and that shows that my function g is a bijection. That means the cardinality of ZPR and the finite field are same, and that proves this theorem. Okay. So, we have proved that you give me any finite field with characteristic p, it will have p to the power r number of elements. Now, let us see how exactly we can construct finite fields for any given p to the power r, where p is a prime number. Okay. And this is very interesting, because it says the following: you give me any prime number p, I will show the existence of a finite field whose characteristic will be that prime number p, and the number of elements in the field will be p to the power r. Okay. And how exactly we construct such a field? So, for constructing such a field, we will take the help of some irreducible monic polynomial, where the coefficients are over Zp and the degree of the polynomial will be r. Why r? Because r is also given as part of your input. So, you are given a prime number p and a value r. My goal is to show the existence of a finite field with characteristic p and with p power r number of elements. So, to do that, I am basically taking a monic irreducible polynomial with coefficients over Zp whose degree is r. Now, if you are wondering whether indeed such polynomials always exist for any given r and p, the answer is yes. Such polynomial always exists for every r and p. Okay. And there are some standard methods for doing that, getting such polynomials, but for some well known values of p and r, such polynomials are publicly available. Now, my goal is to construct a field f. So, my set f will be the set of all polynomials with coefficients over Zp modulo kx. In other words, basically the set f is the collection of all polynomials of degree 0, degree 1, degree 2, degree 3 and up to degree r minus 1, where the coefficients of the polynomial are from Zp. So, in general I can say that f is the collection of all polynomials of degree at most r minus 1. So, this means degree is at most r minus 1, where the coefficients are allowed from the set ZP. Why I am saying it is at most r minus 1, because since each of the coefficients are from the set ZP and my ZP have the elements from 0 to p minus 1, that means I can have a polynomial where all the coefficients are 0. That means I can also have a polynomial which is the 0 polynomial. So, it is not necessarily the case that a of r minus 1, namely the coefficient of the r minus 1th power of x is always supposed to be there, it can also be 0. Okay. So, it turns out that how many elements I can have, how many such polynomials I can have in my collection F, since I can have each of the coefficients taken from the set ZP, namely each of the coefficients can take p possible values and each of them are picked independently. So, that means it is not the case that the coefficient A1 depends on the coefficient A0, it is not the case that the coefficient A2 depends on the coefficient A0 and A1, they are picked independently. So, I can say that from the product rule of counting, there are p to the power r number of possible polynomials in my collection F. So, I have defined my collection F, now I have to give the definition of the abstract plus operation and the abstract dot operation. So, my plus operation here is defined to be the addition of polynomials where the coefficients are added as per ZP, namely addition modulo p, and then I take the resultant polynomial modulo the irreducible polynomial. So, that will ensure that my resultant polynomial will have coefficients over ZP and its degree will be at most r minus 1, because the degree of kx is r. So, if I reduce any polynomial, even if the to begin with, my ax and bx polynomials, both those polynomials will have degree r minus 1, and if I add any two polynomials of degree r minus 1 at most, I will still obtain a polynomial of degree at most r minus 1. So, in fact, I do not need to take a modulo kx, because in the sense the effect of modulo kx will not take place. And my multiplication operation is defined to be the product of two polynomials, the corresponding two polynomials, where the coefficients are multiplied with respect to ZP, and if the degree becomes more than r, I take modulo kx. That is my definition of the abstract plus operation and the abstract dot operation. And my claim is that the way I have constructed my F and the way I have defined my plus operation and the dot operation, this satisfies the properties or they satisfies the field axioms. It can be verified easily. To check specifically, I want to show you that any non-zero polynomial here will have a corresponding multiplicative inverse. Otherwise, remaining properties are easy to verify: the closure, associative, distributive law, existence of identity elements and so on. The additive identity element will be the 0 polynomial, the multiplicative identity element will be the constant polynomial 1 and so on. Let us see the existence of multiplicative inverse. So, imagine you are given a non-empty means non-zero polynomial. I want to show it has a multiplicative inverse, and the multiplicative inverse is guaranteed because of the following. Since I am taking kx to be an irreducible polynomial, so till now you must have been wondering that why I am taking kx to be irreducible, why can't I take kx to be any polynomial of degree r? There is a reason. If I take kx to be irreducible, then I know that the only monic GCD of Ax and Kx will be the constant polynomial 1. Why so? Because since Kx is irreducible, I can't factorize out Kx. That means I do not have non-constant factors of Kx, and hence the only possible monic GCD, the common divisor of Ax and Bx, could be the constant polynomial 1. That means I can say that I can now apply the Euclidean GCD theorem. And as per the Euclidean GCD theorem, the GCD can be expressed in terms of the individual polynomials itself. So, my individual polynomials are Ax and Kx. Then as per the Euclidean theorem, I I can find out linear combiners in quote unquote. They are actually not linear combiners, they are some polynomials when multiplied with Ax and Gx respectively and added will give me the GCD, where the GCD in this case is 1. And what can I say about this multiplier polynomials fx and gx? Each of them are actually polynomials over the field Zp, right, of some degree, need not be of degree at most r minus 1. Now, if this is the case, if this equation holds, then if I take modulo kx on both LHS and RHS, then in my RHS 1 modulo kx will give me the polynomial 1 itself, whereas in my LHS if I divide the LHS by kx, then the effect of kx and kx cancels out, kx is completely divisible by kx. So, overall I get that the product of Ax fx modulo kx will give me the constant polynomial 1, and in other words I have found here 2 polynomials which when multiplied modulo kx will give me 1. So, I can say that fx can be treated as the multiplicative inverse of Ax. Now, if fx has degree up to r minus 1, at most r minus 1, well and good, but if that is not the case, I can reduce fx modulo kx and that will give me a polynomial of degree at most r minus 1, which when multiplied with Ax will give me the identity element 1. So, if you see here closely, what the way I have argued about the existence of multiplicative inverse for Ax polynomial is precisely the same in which where actually when I showed that if GCD of 2 numbers a and n is 1, then we can find out multiplicative inverse of a, and there we argued that as per the Bezoos theorem I can express the GCD of a and n in terms of linear combination, in terms of their linear combination. So, say S and T are the Bezout coefficients, and then I do a mod n on both the sides and I get S times A modulo n is 1, and then I say that A inverse is actually S modulo n. That is what we did in our number theory. The same thing we have generalized in the context of polynomials here. Okay, so that is a general template for constructing a finite field for any given p and r, where the order is p power r. Now, let us see how exactly this framework can be applied to construct fields of various p to the power fields of order p to the power r for some given values of p and r. So, imagine I take p to be 3 and r to be 2. So, I need a polynomial, irreducible polynomial of degree 2. So, this is an irreducible polynomial and my collection F9 will have all the polynomials over Z3, namely the coefficients are from Z3 and the degree of the polynomials can be 0 or 1. So, I get total 9 such polynomials and my plus operation and multiplication operation will be defined modulo x square plus 1. If I want to construct a finite field of order 4, so characteristic should be 2. So, I will take a polynomial, irreducible polynomial of degree 2. So, if you take this irreducible polynomial and this to be your F4 set, then my plus and dot operation will be defined modulo this irreducible polynomial and so on. Okay. So, with that I conclude today's lecture. Just to summarize, in this lecture we continued our discussion regarding the properties of finite fields and we proved a very nice property about the order of a finite field. We showed that the order of a finite field is always of the form some prime number is to the power r, where the prime number is actually the characteristic of that field. Thank you.